Hu Tao, I'm curious about this concept of load balancing you mentioned. Why is it so critical for handling user traffic?
I. Load balancing is like orchestrating a grand concert. Imagine all the sound focused through one tiny flute, it'd get overwhelmed. So, with load balancing, we ensure each part of the system carries some of the load, preventing any single point from collapsing.
So it's about making sure no single system becomes overwhelmed.
Exactly. When you have millions of requests bombarding a service, relying on one machine is like asking a single player to handle an entire orchestra's performance. It's not just impractical, it's downright dangerous.
Dangerous? What happens if a single point fails?
Well, if that single point fails, the entire system can come crashing down like a conductor dropping their baton. No music, just silence, or in this case, no service, just downtime.
I see. How does load balancing prevent this from happening?
By spreading the traffic across multiple systems, like having each musician play their part. So if one musician happened to be out of tune or drop their instrument, it wouldn't ruin the entire performance.
And this distribution of traffic isn't just at a local level, I assume?
That's right, it's done at a high level across data centers. Each data center can be thought of as a section of the orchestra, handling specific types of requests optimally.
Why is that high-level distribution important?
Because it lets us manage traffic efficiently and ensures that if one data center faces issues, others can pick up the slack. It's a safety net, a protective barrier against failures.
Does this mean there are different strategies within load balancing?
Oh yes, the strategies vary greatly based on needs and scenarios. It's not a one-size-fits-all kind of deal. Each scenario is like a different musical composition, requiring its unique arrangement.
What are some of the fundamental reasons for deploying these strategies?
To reduce latency and enhance system reliability and availability, think of it as ensuring the audience always hears the music exactly on time without hiccups.
Latency sounds important. Is it the main focus?
One of the main focuses, yes. Latency is critical when users are waiting for responses, like a violinist hitting their note precisely as the conductor signals.
And reliability, you mentioned that too. How does load balancing increase reliability?
By reducing the risk of a total outage. If one machine or data center fails, others keep the system running, like having backup singers ready to step in if one is under the weather.
It's fascinating how traffic is distributed so effectively. How do you ensure efficiency all the time?
Well, efficiency depends on constant monitoring and adjustments, like a conductor fine-tuning each part of the performance to ensure harmony. We use metrics, software, and algorithms to adapt the system dynamically.
Software and algorithms, you say? What role do they play?
They are the unsung heroes. They analyze data traffic patterns and automatically adjust resources to achieve optimal flow, much like a sound engineer adjusting the levels during a concert.
That's quite complex. How do you manage these adjustments across data centers?
Through a set of predefined rules and sometimes machine learning algorithms. They help decide which data center is best suited to handle specific requests, keeping the performance consistent and efficient.
So these methods adapt in real time?
Yes, indeed. Just like a live performance, everything is happening in real time. Our goal is to ensure that users experience uninterrupted and smooth service.
That must require quite an effort, considering the amount of traffic handled.
It's a challenge, but also an art. With well-tuned systems and skilled engineers behind the scenes, we keep the melody alive.
Such a well-coordinated effort must come from solid planning and consistency.
Precisely, it's all about having a solid foundation, like rehearsals before the big performance, to manage unexpected surges or disruptions seamlessly.
Intriguing. So what happens when a section of this orchestra needs fine-tuning or encounters an issue?
In those cases, just like in a live concert, we might switch to backup systems without missing a beat, ensuring users aren't left hanging.
That kind of seamless transition is impressive. Ensures quality doesn't drop.
Exactly. That is the magic of load balancing at work, a combination of precision, foresight, and artistry.
It's like an endless performance where each note matters. Do all data centers utilize standardized strategies? or do they vary?
There are standards, but flexibility is key. Adaptation to the unique needs of each region, considering latency, resource availability, and capacity, is part of the process.
So, apart from preventing failure, does load balancing enhance user experiences?
Absolutely. It means faster response times and better resource utilization. Everything users see and interact with becomes as smooth as a melody in harmony.
This interconnectedness is making so much sense. Each component plays its role just like musicians in an ensemble.
Yes, and just like an ensemble, every piece must work together perfectly to create a successful performance. That's why we emphasize these strategies so strongly.
I'm eager to explore more. What follows this introduction to load balancing?
We will delve into more specific strategies, analyzing the layers beyond just the high level, just like studying each musical piece to understand its depth.
I look forward to understanding these intricacies. The journey seems as fascinating as the concepts themselves. Hu Tao, I understand framing load balancing towards multiple systems, but why can't one super powerful machine do the trick?
It's a bit more complex than it sounds. Even if we had the world's most powerful computer, we'd run into physical limitations.
Physical limitations? What kind of limits are we talking about?
Well, for one, there's the speed of light. It might sound strange, but the distance data travels affects how fast users get what they're asking for.
So it's not just about having power, but also about how quickly data travels.
Exactly. And that ties into concepts like latency and throughput. Think of latency as how quickly an audience hears a note after the musician plays it.
Latency seems crucial when speed matters. Are there situations where speed is not the primary concern?
Yes, like video uploads. Here, throughput. The volume of data processed over time matters more than just speed.
So for something like search requests, minimizing latency is key, correct?
Correct, it's about delivering results as fast as possible to the user, like a speedy ninja delivering a message.
Interesting. How does that differ from routing video uploads?
For uploads, we focus on throughput. Even if there's some delay, we ensure the data uploads in full and without a hitch.
And this requires a different routing strategy, I assume?
Exactly. The routing strategy changes based on what the user is doing. We might use underutilized routes to handle uploads, maximizing data flow.
This must entail optimizing resource distribution as well.
Yes, factors like user proximity and resource availability are crucial. Imagine directing each request to its most efficient path.
Do these optimal paths change?
Constantly, it's like a dance, always changing with traffic patterns and system conditions.
How do you decide what balance is optimal for each case?
It depends on the hierarchy of the problem, whether it's on a global scale involving multiple data centers or within a single data center.
So handling requests globally versus locally requires different approaches.
Absolutely. Globally, we send requests to data centers with the shortest round-trip time to users for low latency.
And locally, within a data center, does the focus shift?
Yes, we assume machines are equally close to users, focusing more on load distribution and resource utilization.
Does everything boil down to just latency and throughput?
While they're fundamental, balancing also involves factors like maintaining cache efficiency, managing non-interactive traffic, and avoiding congestion.
These additional factors add layers of complexity to the balancing act.
Definitely. It's not a simple task. It's intricate and requires constant adaptation, just like a lively performance.
Intriguing. Different requests, different needs, and thus different paths.
Precisely. And each path must be managed to be as efficient and effective as possible. It's like balancing on a tightrope.
I'm learning so much from your insights, Hu Tao. What you describe sounds like a grand choreography of network magic.
Haha, and just like choreography, it takes a bit of flair and an awful lot of practice to pull off without, falling flat on your face.
Hu Tao, you've been teaching me about load balancing, and I'm curious about DNS load balancing. Can you tell me more about it?
Absolutely. DNS load balancing is like the opening act of a concert. It's the first step in directing user traffic before they even connect to our services directly.
Why start with DNS? Is it simpler than other methods?
In many ways, yes. DNS load balancing is simple because it happens before a connection is established. But simple doesn't mean without challenges.
Challenges. What sort of challenges are you talking about?
Well, the indirection introduced by DNS resolvers is a big one. Users don't talk to our servers directly. Instead, they often go through something called a recursive resolver.
Recursive resolvers, like intermediaries in this process?
Exactly. They act as intermediaries and cache responses, which makes predicting how DNS replies will impact traffic a bit tricky.
So does this caching affect the load balancing decisions you make?
Yes, it adds a layer of complexity. For example, a decision we make might reach a single user, or thousands, depending on the caching behavior.
How do you manage to mitigate these challenges with caching and indirection?
One strategy is using anycast DNS addresses, which helps direct queries to the nearest server. It's like adding arrows to guide the way.
That sounds useful. Does it ensure messages are sent closer to the user's location?
Exactly. By routing to the nearest data center, we reduce latency and make the service as snappy as possible.
Given these complexities, how do you handle the randomness of client behavior?
We try to optimize DNS replies by maintaining geographic mappings. This ensures requests are largely sent to the best possible locations.
Sounds complicated. How dynamic is this geographic mapping?
It's quite dynamic. We constantly update it based on traffic patterns and user distribution to keep it accurate.
Keeping everything up to date must be a continuous effort.
Very much so. An ongoing symphony of adjustments to ensure that users always get the best experience.
And what about non-deterministic reply paths you mentioned? How do those factor in?
Non-deterministic reply paths mean the journey from a user to our data center isn't always predictable. We mitigate this by analyzing the paths and adapting.
This almost sounds like navigating a maze with ever-changing walls.
That's a great analogy, Each step requires reassessment to find the optimal path.
This must require a lot of coordination and foresight.
Coordination is key. Each part of the system must understand its role for the overall flow to remain smooth.
And what happens if things don't go as planned due to caching?
We account for that through traffic analysis. It's like gauging the audience's reaction to tweak the performance as needed.
Do you ever use feedback loops to improve DNS load balancing?
Definitely, feedback informs us where tweaks are needed. Another example of how we ensure all components harmonize.
That's really complex, but seems rewarding when it all comes together.
It's like hitting that perfect note in a song, satisfying for everyone involved.
What's next after DNS in the grand scheme of load balancing?
Next up, we look at load balancing using virtual IP addresses. It's another fascinating layer in our process.
I'm eager to dive deeper into that, Hu Tao. This dance of data across networks is endlessly intriguing.
Get ready for more twists and turns, It's going to be quite the adventure.
I look forward to learning about balancing that dance through virtual IPs. Hu Tao, you mentioned virtual IP addresses for load balancing. How does this method work in practice?
Well, I think of a virtual IP address or VIP as a conductor's baton, not tied to one musician. It's shared among many musicians, or devices. From the user's perspective, it seems like a single address.
That sounds efficient. But how do devices decide which ones should handle a request?
That's where the network load balancer comes in. It's like a stage manager, directing packets to the correct performers behind the VIP. Each backend processes the request like it's in the spotlight.
How does the balancer choose the appropriate backend?
One approach is to send requests to the least loaded backend, but for stateful connections this is tricky. Instead, we sometimes use consistent hashing.
Consistent hashing? How does that ensure stability?
With consistent hashing, the mapping of requests to backends changes minimally when nodes are added or removed. So, most connections remain undisturbed, unlike a musician abruptly leaving mid-performance.
And if one backend fails, how is this managed?
It's simple with consistent hashing. It adjusts mappings while minimizing disruptions, keeping the music, service continuous.
What about the data path? How do you manage traffic without overwhelming the load balancer?
We use direct server response DSR, where the backend sends responses directly to clients bypassing the balancer. It's efficient, like musicians playing directly for the audience.
Doesn't using Layer 2 for DSR at scale cause issues?
It can. All machines must communicate at the data link layer fitting within a single broadcast domain. It's challenging as we grow, as if the ensemble keeps adding players.
How do you handle this complexity?
We move to packet encapsulation, a neat trick. Encapsulating packets with another IP layer allows networks to flexibly grow without being on the same stage.
Does encapsulation affect packet size?
Yes, it adds overhead, which can cause exceeding size limits and require fragmentation, like adding excess notes to a song.
How do you avoid fragmentation once packets are in a data center?
We use a larger maximum transmission unit MTU size, supporting larger packets, but it's crucial for networks to handle this.
So addressing these challenges, does it enhance flexibility?
Absolutely, encapsulation allows us to design and evolve networks without getting tangled in limitations. It's like expanding the concert hall with limitless capacity.
This expansion across continents must be quite the task.
Indeed it is. We balance performance and capacity across regions, ensuring the music never stops no matter where it's played.
Incredible. Each layer of this system is like an intricate composition.
And each component plays its part to keep the concert seamless. That's the art of virtual load balancing.
I feel like I've been part of a journey across stages of a grand performance. What's next after virtual IPs?
Next, we dive deeper into ensuring continuity and resilience against unforeseen disruptions, always ready to keep the show going.
Thank you, Hu Tao. Each layer we've explored adds more depth than I'd expected.
My pleasure, There's always more to discover beneath the surface of this technical symphony.